afternoon, everyone. I am really honored and excited to introduce the two gentlemen that are going to be up here today talking to you at our panel discussion called The Earth and Stars. First will be Terry Wallace, Dr. Terry Wallace, who has been a long-time mineral collector and just retired. It's been weeks or months anyway, very recently retired. Terry was the director of the Los Alamos National Laboratory. Also today speaking to us is Dr. Peter Modreski. Pete has been a geologist with the United States Geological Survey for 41 years. So we have two very, very expert presenters to us today. And first, let me present to you Dr. Terry Wallace.
Good afternoon, and Pete and I are going to try to convince you that minerals aren't just about pretty things today, and so that's our whole object, to be able to get this. And, I think from some perspective, if you look at minerals, they fascinated man for thousands of years. The earliest reference to sort of a mineral collection I can find is a Sumerian tablet, and the cuneiforms actually describe the brilliance of a gold nugget with a stream running over the top of it. And I think it would be real easy to imagine this ancient historical fascination in terms of beauty, something that's really beautiful. But I would posit that that's far more complex than that. If we kind of think about things, and you think about anybody that's picked up a sharp edge of a quartz crystal, the perfection in that crystal, or maybe the deep blue color of a lapis sprinkled with some pyrite on it, or even the heft of a native piece of lead, sparks the imagination far beyond what we might think of as conventional beauty. We ask the question, what's the story of these minerals? What do they mean? And I would posit, again, that when we look at this, they actually do contain a story which is complicated and goes back to the very beginning of the universe, tells you something about how our solar system was formed, certainly gives a geologic story about what's happened on Earth. And you put all that together, and I think of something that's really very, very detailed in terms of what this mineral collecting, if we were interested in it. I like to talk about this concept of forensic mineralogy, and what I really mean by that is that minerals themselves sort of act like the DNA of the planet. They contain fragments of our complex history, from its formation 4.5 billion years ago, the creation of a planet that's covered by an ocean, the oxygen-rich atmosphere that gave rise to life. Today there's 5,700 identified mineral species, and they represent a variety that's unparalleled, certainly even in our solar system. When we look out there, we may not be able to be picking up all the minerals in every planet when we look at it, but we're still 100 times more minerals on Earth than anywhere else in the solar system. There's something very unique about our planet, and being able to look at these minerals in detail, we can learn something pretty unique. I think that surely we think about minerals as being one of the most interesting collectibles. There's hundreds of thousands of assemblages of specimens that people put together, many of them even in this hall. And they cover the whole spectrum of mineralogy, from people that collect really pretty rocks and call them objects of art, to those collectors which only are interested in micromounts and looking at the perfection. And basically, I can't even see the microscope, but I mean, you're looking at this spectrum here. But I'm going to kind of take you on an adventure through why I think of them as DNA as a scientist. And I'm going to just try to illustrate this with 3 quick stories. And the 3 stories I'm going to tell is something about gold and the age of the universe. Then I'm going to talk about the age of Earth from looking at minerals within meteorites. And then I'm going to touch on a more controversial topic to end it, and that is the mystery of silver wires. And so today we're going to kind of explore these things as we go forward and look at what I think of as our DNA. So again, when we think about collecting, these are all, of course, from my collection, which is focused on silver minerals, But it's always been an intersection between science, understanding either the chemistry or the physics or the spectrum of things go together, with history, because every mineral that's collected, somebody had to make the decision to collect that. And so there was a mining activity or a collecting activity, to art, and to finally discovery. So I'm going to start out then again. This is a diagram that's now rather famous. It's around. It's on the right-hand side up here. It shows the evolution of minerals on our planet. So if we look at the beginning of our planet, we probably had somewhere on the order of 40 to 60 minerals during the early stage, the first half to maybe almost 1 billion years of Earth. And then we began to see some interactions with chemistry in the Earth, fractionation, and we began to grow new mineral species. And so I put on some different things there. You could see when plate tectonics began on our planet and so on. But a huge event occurred somewhere around 2.75 billion years ago, and that was the explosion of life. So we probably had life before then, but suddenly life was self-sustaining, and when it did that, it was able to go through photosynthesis, and we produced an oxygen-rich atmosphere. And oxygen we have to survive, but if you're a chemist, you know oxygen is one of the most destructive things out there. And so oxygen basically gives us birth of a whole bunch of new minerals, and as we continue to have other minerals. I'm going to talk about this thing in the upper left-hand picture in just a moment. That's a section of the Canyon Diablo meteorite. It's one of the most famous specimens that probably nobody in this room knows about, right? So this section of the Canyon Diablo meteorite, it was owned by Claire Patterson at Caltech, and he was trying to understand the age of the Earth. And so he drilled all those holes. And all those holes are actually, he's drilling out a little tiny piece of a mineral, which I'll talk about in a moment. At the bottom below that is Simon Chloride, which probably nobody has in their collection here, but it's a mineral that's been recently identified, or in the last decade, in Arizona, and it's only in a certain set of mines. So it is what we call an anthropogenic mineral. It's naturally occurring, but it wouldn't have occurred if we didn't have man. And so this kind of is going to give you a spectrum of the things we put together when we talk about what do we see in our DNA, what do we see about the Earth as we go forward. There's the canyon, or the meteorite crater in the background, and you could see in the horizon is San Francisco Peaks and Flagstaff. This is my section of the Canyon Diablo meteorite, which I am told, but I can't prove, is from the same large section that Claire Patterson's was. I haven't drilled a bunch of holes in it, though. But if you look in the very middle of that, there's a black-looking thing, and that's an iron sulfide. It's called trilite. And the sulfur there has an affinity for lead. So iron doesn't have an affinity, or lead doesn't have an affinity for iron. So in general, it's really hard to see much in meteorites that have to do with lead, which is going to be important. But I can look at the lead that's in that trilite. And that's what Claire Patterson did also. And there's 3 common types of lead that we can find. There's lead isotopes. One lead isotope, 204, is kind of the background. It's what was from the beginning of our universe. And then there's 2 isotopes which are stable, but they're produced by the radiogenic decay of uranium and thorium. But let's focus on uranium. One of them from the uranium-238, the radioactive uranium we use to make atomic bombs, and uranium-235, which is the much more common type. But if we look at the ratio of those decays, because they have different half-lives, and the background, we can begin to get an idea what that age of the Earth is. So from Claire's work there, you see all those holes. I'll over here is the decay sequence for uranium-238. It's a complicated thing. It starts out as uranium-238, then it goes to thorium, and then it decays through a series of things which are radon and radium and so on, and finally to the stable thing that's down here, which is this lead isotope at the bottom that you can see here. So if I go and take these and I compare the isotope that I see for this uranium-238, know what its half-life is. Its half-life is about 700,000 years. And I compare it to the uranium decay product that I get from 235, which has 238 is 4.5 billion years. 235 is 700,000 years. And I know what the background is. Lo and behold, I can put that together in one diagram, and I can determine the age of the Earth. So Patterson did this in 1955, so right before I was born, and he came up with an age of the Earth of 4.54 billion years old. So we've had a long time and much better instrumentation to figure out what the age of the Earth is, and we still accept Claire Patterson's number to 3 digits. A remarkable work. So here's a case in which, when I say DNA, it's an example of looking at what's in a mineral that tells us something about our history. It tells us about when our clock turned on for our solar system. So we can date our solar system quite accurately by looking at some impurity, in this case in a mineral. I'm going to come back to that a little bit, but then I want to go stretch a little further back and actually look at the beginning of this universe, okay? So I can start the age of our planet, but to put it in context, let's go back and look at gold. So what does gold have to do with the age of the universe? Well, when we make the elements, and we'll talk about that quickly in terms of what we call nucleosynthesis, production of stars and everything else, we go through these processes of gathering gases and squeezing them together and making stars. But some minerals are just too heavy to do simply. We have to have incredibly rare and dynamic processes. And gold happens to be one of those. So when you find these wonderful gold specimens on the left-hand side of these specimens that come out of Mato Grosso from the western Brazil, starting in 2015. On the other side is these new crystallized golds that came out in the last year and a half in Morocco. We're spellbound because it's a wonderful gold specimen, right? But in there is the same kind of DNA that we just saw for the meteorite and the trilite to tell us something about what's happening on Earth. So I'm going to take us, this is the stuff of the Big Bang. This is my little loop of life for gold. And it starts with the Big Bang. That Big Bang then starts with producing a bunch of material, which I'll go through. And then we're going to find out that we have to have some other exotic things happen. In this case, it's going to be a neutron star collision. And it's going to spew out stuff through the solar system, which eventually has to recollect because of the magic of gravity. So gravity isn't the thing that bothers you every day when you step on the scale. It also is really good because it collects stuff, and we make our solar system. Finally, plate tectonics recollects that gold, and we have some miners, these two exotic guys in their very good-looking fur coats, or Yukon miners, that collected that material. So gold, where did it come from? So the Big Bang is always something that's a mystery to everybody when we talk about it. And it doesn't matter whether you're talking to Stephen Hawking or you're talking to Terry Wallace, everybody asks the same question. Okay, you're going to tell me about the Big Bang. I want to know what happened before the Big Bang. Okay, you can ask me that, and I'll tell you the same thing. Nothing. Okay, so that question's answered. All right, we're going to start with this thing that's called the Big Bang. And the Big Bang, of course, we just had this sudden explosion of material, very, very hot material. In the fraction of a second, we spewed forth an enormous amount of material, but it would be material which you would not recognize. In that these were all fundamental particles that make up electrons, protons, neutrons. So we call them hadrons and leptons and things like this, quarks. All right? And these materials so they haven't made even electrons or neutrons yet when they're spewed out here. And it's so hot. It's basically in that small fraction of a second. The material is on the order of 50 billion degrees. Okay, so no material can sustain in building particles. But we spewed this out, it begins to expand very rapidly. As it expands, it cools. And so we finally make some protons. And then when we make protons, those protons sometimes interact and we make our first atoms. And those first atoms are going to be hydrogen and helium. Maybe we make a little lithium. But for 100 million years, it's still spewing out, that's all we're doing. But it's finally cooling down enough that this new material is this soup of hydrogen and helium, but it's not a uniform soup, and that was the key. And so one of these strange forces in the universe is gravity. And since it's not uniform, enough of the material could be in a clump that begins to pull other material towards it. As it pulls that other material towards it, it compresses it, and we build our first star at 100 or 150 million years. And then we begin to do really cool stuff. And in those stars, we begin to make a whole bunch of new material. We make our first mineral probably around 300 million years. The very first mineral is a diamond. So, if you go out and collect a diamond, you're thinking about, oh, wow, this is pretty cool. And this is, something that De Beers has marketed as the perfect scam forever. But actually it is good because it's the first mineral that we're going to see in the history of the universe. And we're going to begin to have enough of these stars that they have gravitational attraction on each other. So we begin to give our earliest galaxies, and we're going to begin to have stars begin to collide. They're going to begin to do a lot of other stuff. And finally, we're going to have our star form about 4.6 billion years ago. So gold's really tough to make. Let me remind you what gold looks like. You all remember when you were in high school and you finally had a physics or chemistry class, and they showed you what an atom looks like. And so they showed a nucleus, and then they showed circular orbits for where the electrons were. And they said that in the nucleus we got protons, and out here we got electrons, and like magnets have a negative and a positive polarity, they can't interact, right? Of course, that's nothing what an atom actually looks like, right? So let me give you an idea. We're going to talk about gold. How does a gold atom actually look like? Let's take the nucleus of a gold atom. It's going to have 79 protons, and I have a bunch of neutrons, more than 79, but a bunch around there. And it's going to have electrons around here, but they're not in a circular orbit. They're defined by energies, and so they're just kind of moving all around. But if I was able to go lay it out in a scale you could see, I would need a football field. And on that football field, in the very center of that football field, would be a head of a pin. That would be the nucleus. And the electrons that are all coming around here would be as far as the in zones. Okay, so it's empty space, even if it doesn't seem like empty space. But that empty space is empty because of all these interactions between the electronic forces of the protons and neutrons, but also forces that you don't think about very much, which are called the nuclear forces, which allow the protons to be next to each other. So if I have two positive protons, if I think of them as magnets, how could I ever stick them together? And there's nuclear forces that allow you to do that, but they're competing with all this other stuff. So in your mind, think about this. In gold, it's really tough to do. If we make a star, let's make our star. And we have this material coming together, and it's a tremendous engine, but it's squeezing. But as it squeezes, we have fusion. We make two things like hydrogen squeeze together, we make helium. When we do that, we release a lot of energy. That raises the temperature, so we want the star to expand because it's getting hot. But the gravity is wanting to contract it. Those competing forces are the things that make our star really interesting. But eventually, as we squeeze and squeeze down, we can squeeze these things down so that we begin to make, through nucleosynthesis, elements as large as or heavy as iron and nickel. We can't make anything any heavier because those competing forces of squeezing things together with the electrons and so on, and the charge forces, we reach a point in which we just can't squeeze them together in our stars. We do not have a star that can make anything heavier than nickel. I already forgot how to do the advance. Oh, there it is. So we call that, again, nucleosynthesis, and we have this wonderful thing that's called the binding curve of energy. And if you come down here, the atomic mass, so that's the number of protons that are in the nucleus, you can see that we have these competing forces, and as we come down, we come to a minimum at iron, maybe right at nickel, but if we get below that, we can't do this in nature. And so the nucleosynthesis, maybe we can add helium, and helium, when we squeeze it hard enough, we can make carbon. We can do that all the way up to iron, but we have a limit in what we can do. Our star will eventually die. And the reason is we've squeezed all the hydrogen into helium. We've squeezed all the helium into carbon. We've squeezed all the carbon into sulfur. And pretty soon we just can't squeeze any more and so we can't produce heat. So the star will collapse on itself. And when it collapses on itself, we have a kilonova or some kind of explosion, but basically we're done making new stuff. If we squeeze it or wait long enough, what's after we've kilonova and we're all done, we're left with one of the coolest things in the universe, period, and that's a neutron star. So we've blown off all this other stuff, but we still got this heavy core, and it's squeezing itself. But now, imagine you took an electron, which is a negative charge, and a proton, which is a positive charge, and we squeeze them so much together, they're going to make a neutron. They can't have no charge. So we end up with a ball of this really heavy stuff, which is neutrons. All right, so our Earth will eventually collapse to the size of being about 12 kilometers. And it will be basically this wonderful goo of neutrons. And it's so massive that if I take a single tablespoon out, it's 10 million tons. So our present star, if I go out and I do the same tablespoon, it's only 8 pounds in my tablespoon. It's a lot, but it's nothing compared to 10 million tons. Okay? Very massive, small object. We've got a lot of neutron stars in our universe. And they're affecting all the other objects because they have high gravitational potential. So if I'm out here and I'm my own neutron star, and there's a neutron star in my neighborhood, maybe only a few billion light years away, I'm probably going to actually begin to feel it. Given enough time, we'll slowly spiral into each other. So just go back to, this is the classic definition of the way gold looks. Remember I told you it's actually mostly empty space? I just reminded you, you have all these electrons, you got the core. There's lots of things that are really interesting about gold themselves will be DNA, but I want to just focus on this fact that we've squeezed all these things together to make this neutron star. And we'll come back to some of this later on. The way then we do this is if we get a neutron star, nothing's happening, we can't make any heavier elements, but we've learned in the laboratory if we take an element, we can't maybe nucleosynthesis squeeze it, but we shoot some other neutrons into it, the neutron will add mass, and the neutron decays into a proton, an electron, and a neutrino, but we won't go into the neutrino stuff, all right? So we can make a heavier thing then, but it's rejected in most of the processes unless we have a real extreme environment. That extreme environment is what we call the rapid process, or the R process. So if we could take a nucleus of any atom and I could just start shoving neutrons in really fast before they can decay, I can make new elements. But how do I do that? Well, the way I do that is I have two neutron stars run into each other. So I'm going to look at a very violent collision between this mass of neutrons, and we're going to see that if we bring them together, they're going to flood together, and if there's a seed of a carbon or any other thing that's left around, I can begin to make the heavier elements. And so I'm going to talk about a particular neutron star collision that occurred in 2017. And we actually could capture that on what's called LIGO. It's a long-range, basically, yardstick between Louisiana and Washington, and we watch that yardstick stretch or contract, which is telling us what the universe space around you looks like. When you bring two heavy objects together and they collide, it causes a disruption in space, and it propagates out like a wave. We call this a gravity wave. So if I have these two things come and collide, I'm going to make this extreme forge to be able to construct new material. And in this case, when I collide these together, I can flood something so much that I can make heavy elements. In fact, most of the heavy elements are made through this process. We'll find out that when we saw this in 2017, we happened to be able to know where it occurred. We had taken pictures in the previous month before. It's before the collision in this particular area, so we can use spectra, and we can actually see the ejection of platinum and gold from a neutron star collision. And the total amount of platinum from this neutron star collision is roughly 900 Earth masses of platinum that were created in this instant of time of collision, and about 500 Earth masses of gold. Platinum is more stable than gold in this process, so there's actually more platinum in the universe than gold, but different story there coming. I want to just show you where this is captured after this neutron star collision was found by this yardstick. We knew where it was in space. It came back. You see one neutron star and the bright neutron star there are coming together, and they collided on the 21st of August, 2017. This was the spectra. Again, I don't expect anybody to know what that spectra really looks like, but it's visible light, wavelength versus its intensity. And this is a picture, this is actually a cartoon, not a real picture of the ejecta that's coming out, but we can assign the elements that we're done. So here we are, we found a way to make gold, okay? But it spewed all the gold out into the universe. Do you know how big the universe is? Okay, so it went out to what we call the interstellar space. The interstellar space has mass in it. But most interstellar space, if I'm going to capture a cube here and compare it to sea level here, and I just look at the number of atoms, doesn't matter what they are, the number of atoms in a little vial here versus a little vial here that I've got at sea level at Earth, this one has 10 to the minus 20th number of atoms as compared to our normal sea level. I mean, it's an unimaginably small number, all right? There's gold out there, but it's a long ways away. But we have time and gravity on our side. So even though it's spewed out there, that cloud, that material will not be uniform, and eventually it begins to compress back in. Collects that gold back in, collects that platinum back in, collects the hydrogen and everything else. And we begin to form, for example, our star. And so when this cloud, comes together, we begin to form our solar system. And you can see as we do this, it probably took on the order of 5 billion years to begin to put this material. But once we got it close enough, we made our star. And in 50 million years, we made a star. We separated out material. We made our planets. And we made our solar system. So what did our solar system stuff look like? As we put this together, we're bringing this material together, and it's a very violent process. Okay, as you squeeze this together, you may have a rocky piece of regolith from somewhere, a clump of maybe ice, and when they collide, it produces heat. So the analogy for this is, and I expect everybody to go home and practice this, if you go play billiards, when your billiard ball hits the other billiard ball, they actually can heat up about 1.5 degrees Fahrenheit. So I want you to all go do that and feel if you can feel that. I doubt you can, but anyway. But when you do this 1 billion times as you build your planet, you make a very hot mass of material. And that hot mass of the material is like a pot. And so that pot is able to separate out the elements, and we begin to build a planet that's fractionated. So we got a core, it's primarily iron, but it's got a lot of gold and platinum in it, by the way. And we make our planet. But when we made our planet, we took all this gold, but we didn't leave it at the surface. We put it in the core. But luckily, all these other little planetoids began to collide with us. We started plate tectonics. And so we made a giant spoon to stir in the earth, and we bring some of that gold to the surface. This is elements in the Earth's crust, and so all those things that you see there are basically elements. The thing in the yellow is what we call the rarest of the metals, and so they're way low abundant in the crust because most of it's in the core. But they're way higher than most of the crust. So something has been able to put some gold and platinum there, and that's an interesting plate tectonics process. There's another fragment of our DNA. Plate tectonics is unique on Earth. There are no other planets in the solar system with plate tectonics. There's volcanism, but no plate tectonics. So they're screwed. They are never going to have good-looking minerals. But we can see that in our minerals. So the gold that you saw there in the very beginning when I talked about Brazil was resorted, put together, and plate tectonics allowed it to build a deposit. In this case, it was beneath a series of stratovolcanoes that have long since gone away, between a collision between what became South America and Africa and the construction of Pangaea 800 million years ago. I could take any one of those gold crystals, by the way, I just told you how much empty space it is, and I can tell you when it was melted. How do I do that? Because they always have a little uranium in them, and when uranium decays, it makes helium. So if I can find uranium in it, and I can find the helium, I can have another atomic clock to tell you exactly how old that gold was when it was melted. So nobody can make a fake old gold artifact anymore, by the way. We can date when they were molten very, very accurately today. But, and so in this case, I could see that these were made 800 million years ago. And it was exactly when we had this collision between Africa and South America to make Pangaea. There's another segment of our DNA. We're actually beginning reconstruction. This is a really strange place because usually when mountains erode, okay, the gold becomes placer and it rolls downstream, and you end up with attractive, but they're nuggets, right? So they're not sharp crystals, and that was not the case here. Let me just tell you a little bit about another strand of DNA. How do crystals grow? So we can imagine when a crystal grows, we have competing forces. The crystal wants to grow because we have a solution. So everybody has ever had to have a kid go do a science fair project in the 3rd or 6th grade, we all grew alum crystals. Okay? It's just like a rite of passage. And what we see is a seed on a string. And that seed on the string has the solution around it, and it changes an energy condition to make the crystal grow. It minimizes the energy. But it's more complicated. How fast is that solution moving? What is the temperature? We call those driving forces. And so we actually see that when crystals grow, they can grow. If they're slow, they make very, very smooth crystals, which we call our polyhedral. If they grow fast, the edges capture things more quickly, so you end up with Hoppered crystals. Or if they grow really fast, we end up with dendrites. So we can actually also tell how long things take to grow. So when I look at these gold crystals from Brazil, I see Hoppered crystals. And actually, if you look over at that last one here, you're actually looking at going from an octahedron to a cube. The last one is just a section of a cube. So this is actually still a single crystal, and you're looking at the hoppers stacked up. Okay? And so I can tell you now the individual crystal size, and from some simple calculations that require a supercomputer, I can tell you that that crystal probably grew in about 7 minutes. So now I have another strand of DNA about my processes in Earth. We used to think when things grew and we got giant crystals, that meant that they were there a long time. Actually, most of the crystals we see in Earth that are really collectible grew in hours or maybe days. And Pete will correct me later on. So I'm going to leave with that one and come back to another element that's dear and near to my heart, and that's silver. So what does this tell us? Another DNA strand. You know, silver often you'll see is spectacular wires. So it's one of these things that you see these wires coming out. This is a mineral from Sardinia, or a specimen, and that's a canthite at the bottom, and then you see the silver wires that come out. And the upper diagram that you see there is a paper that was published in 1836, in which these silver wires were known to grow out of a canthite. Actually, we can go way back in history and see this was observed for a long time. So we know that wires grow out of this. How they grow and why they grow has been something that we've learned much more recently, but will give us some insight into this, as I said, another DNA strand. The very first person that published about silver growing out of a canthite, although he didn't call that, was a paper that was published in 1574. And in this case, they had a large table and a person, for reasons that I don't know, was cutting the acanthite with a sharp knife. And they would lay it out on a sorting table. And out of this cut acanthite, silver wires would bloom over time. And what they were looking at is a changing physical condition. And it turns out it has to do a little bit with acanthite being a polymorph that if you change temperature, it goes from monoclinic to cubic in a slightly different spacing. Okay, detail that we could spend a lot of time on, but let's come back and look at this. These are synthetic silvers. The first one over here is a famous experiment in which a guy just basically used a pizza pan and put in acanthite, and he went to 400 degrees C, which is well above the polymorph, and he grew these wonderful silver wires out. These silver wires aren't big. The other one was a very famous marketed specimen where all the Moroccan silvers that came out 12 years ago were bright and shiny, but if you actually turned them over and looked at them, there were torch marks on the bottom. And we know now that they were basically man-made in that they took acanthite, changed the phase, and then started this production of silver wire, and it grew. And so I would call those non-native. There are people that will still say, well, man was intervened, but it was still natural because the acanthite's natural. So what we're really looking at, as I said, we're going to change the crystal systems, monoclinic to cubic, and this is a complicated diagram. I'm not really going to go into it, but when we change that, we get what's called a Frankel defect. And it allows one silver atom to move. Silver has what I call a promiscuous electron. And so it's willing to leave it behind. But when it leaves it behind, it creates a charge. And that charge pulls the next silver in to fill that defect, the Frankel defect. But when it pulls that silver in to fill that Frankel defect, it leaves another hole which gets filled. And so we grow a wire by pulling this defect out to the surface. So these are acanthites. And again, as we do this phase change, we can grow silver out of this. Thank God we don't always do this, but there are many vacancies. So ask, well, how do you grow the silver wires? The specimen over on the right-hand side is a Guanajuato acanthite that weighs about 1/4 pound. So it's a pretty big acanthite. If I just look at the amount of silver wire and made it into one wire that I can be able to do in a laboratory, I could make a wire that would stretch to here to Washington, D.C. twice. So we can make an awful lot of silver wires by doing this. So you could do it with any mineral that contains a sulfur and a silver. This is a specimen that I own on the far side over there. It's silver wires, obviously, but it's now coming out of argyrodite. Okay, so it's a silver sulfide with some other funky stuff like tin in there. But I can do this on any specimen. So the question is, this is going to occur in nature. I just showed you we could do it in Morocco. What is the genetic part when I'm talking about DNA that I can get from this? Well, an example is we had all these silvers that came out in 1993 from Freiburg. Suddenly hit the market, and there's discussion. Do they have the influence of the man or not? And that's a great question. How would you ever prove one way or the other? These are obviously other silver wires that people didn't question as much. In the middle is a Charnacio wire. The other one's also a Freiburg wire that's from the 1700s. Big one from Kazakhstan over here. No acanthite matrix in that. And frankly, we didn't know how to answer this question for a long time. But economic geologists trying to get rich began to look at a very subtle change in silver. Silver has two stable isotopes. So those stable isotopes we call 107 and 109, so counting the number of things that are in the nucleus. And they're both stable. And it just so happens that nature made it so it's 50-50. If I pick up a specimen, half of them are silver 107, half of them are silver 109. Okay? So if I go look at the different materials, I find that if I pick up this, for most of the materials it's 50-50. But the economic geologists noted that sometimes for high temperature environments, there was missing silver 107, the lighter element. So the question is, why? And the reason is this thing called volatility. So volatility is a little easier to explain if you take something like mercury. So I've got a pool of mercury. Everybody's seen that. If I heat it up, mercury has 3 stable isotopes. If I just heat it for a day, I get rid of all the lightest isotope because a small difference in its mass means that it's more easily to escape as a gas. Same thing for silver. 107, if we get it high enough temperature, is going to leave. So if I look at everything, and so this is the last almost diagram, I got a canthite up there, and now I'm going to do a ratio of silver 107 to 109, where the 0 line is what nature sees most of the time. So if I go over to the right-hand side, I have a lot more silver 109 than I do for most natural things. If I go to the left-hand side, I've got a little less silver 109 than I usually do. So I can see a canthite, silver wires, we have a good historical precedence, coins, everything else. Uh-oh. And then I'm going to go to making all these in the laboratory, and I see way enriched in silver 109 as compared. And then come back here, I can also make synthetic wires at low temperatures if I'm patient enough, and they're not very enriched. Suddenly I have a genetic marker whether temperature was the key to growing that silver wire. So when I look at a silver wire today, I can know that nature did some spectacular things. But when I look at natural wires, they have a much lower concentration or much less enrichment in 109 than 107 because they're formed under high pressure environments. If I squeeze that mercury that I just described in a test tube, it doesn't fractionate because the volatility can't take place. We can't have an atom leave because there's too much pressure. So if we look in most geologic environments, the high pressure keeps us from actually fractionating. But if I do it in the pizza oven on the stove, the 107 disappears. So I leave with this description thinking about the minerals that we think as being wonderfully marvelous things to being the perfect science experiment to tell us what has happened from our Earth from the beginning of the universe to the pizza oven in the end. So thank you very much. And again, we'll let Pete talk on his, and we'll come back to questions.
I'm pleased to be part of this group of presentations here. You know, I guess I've always been fascinated by minerals from back when I was a kid. I guess as I was in high school and such, in spite of my enjoyment of minerals, I was more fascinated by chemistry, and so I majored in chemistry in college. And then when I went into graduate school, I switched to geochemistry at Penn State so I could get back into minerals, and I guess that's been my joy, and that's what I'm gonna talk about here. And after we came up with this title for my talk, I wasn't quite sure what that really meant and what I was going to talk about. And I'm going to you'll see what I'm going to talk about, but I wanted to kind of focus on some of the aspects of minerals and how our understanding of them has grown, so that we know, I'm going to talk about some of the ways that we've learned about minerals over the centuries and decades, okay? It's not really going to be history either, but you'll see, okay? And let me just start. Just thinking a little bit about what minerals are, okay? And it's been fascinating to see the number of known minerals grow over the time that I've known about them and studied them. When I tell people when I was young and I started getting books about rocks and minerals, they would say, there are over 2,000 known minerals. And now that's grown over to 3,000 and 4,000. And a couple of years ago, it was a big deal when the total exceeded 5,000. And talk I'm going to give is going to build on some slides I had prepared for some previous talks I've done. And one of these was back in 2019, and I looked on MnDAT and counted that there were I didn't have to count them, they display the number, that there were 5,512 minerals out of almost 2 years ago. And in January, when I gave a version of this talk, there were 5,600 and some, and I just looked things up yesterday, and I saw we had, depending on which database source you look at, there's 5,720 some known minerals. And I would often tell people that I believe that about 100 new minerals are described every year. And in fact, that looks like it's pretty close to right on, because in 2 years from 2019, there have been a little bit more than 200 new minerals known. So it's cool. There are a lot of minerals. It gives us a lot of things to play with. I just wanted to, hit the wrong button. I was playing around on typing out this slide and thinking about what some of the major minerals that make up the major parts of the Earth are, the major rocks on the Earth. And I guess I'm not getting into the Earth's core, so that doesn't appear here, but I would just list some of the main minerals that occur in igneous rocks and that occur in metamorphic rocks. And they're these are our common minerals. These are the ones that when you're first studying minerals and geology, if you learn about these minerals, you're kind of going to understand the mineral makeup of most rocks you're going to encounter. We're not going to see all these weird, special, pretty, fancy things that we love at the mineral shows, okay? So in igneous rocks, we've got pyroxenes and feldspars and micas and olivine and quartz. And of course, I could have gone on and listing them. I've left out lots of things, magnetite, tourmaline, who knows what. Metamorphic rocks, because some of those primary igneous minerals aren't always stable when you metamorphose them. So we get a lot more water-bearing minerals, for one thing, in metamorphic rocks. So we still have mica and feldspars. We tend to have more amphibole minerals, which are hydrous in metamorphic rocks, than we do in parent igneous rocks. Things like chloride group minerals and a whole bunch of other what we think of as special minerals that form in metamorphic rocks, like garnet and starlite, et cetera, et cetera. And I can go on to other kinds of rocks, sedimentary rocks, those dull things that may contain fossils, but they're usually kind of crumbly and ugly and don't form as many nice minerals, right? So they can consist of some things that have survived the sedimentary, the processes of weathering and erosion, and they can consist of some new minerals that have formed in the sedimentary environment. So we've got, aside from quartz, which is really abundant, we've got carbonates and clay minerals and gypsum and salt and iron oxides and maybe opal, other things. And then there's this whole other category of rocks that I like to talk about, that I tell teachers and students when I give classes that we're really telling them a big lie when we say there are three kinds of rocks, because the fourth kind are the mineral material that's formed in hydrothermal veins that is crystallized from hot water, some of it really hot, some of it only warm, but these are not igneous materials because they were never molten. They're not metamorphosed because they're not turned in from something else by heat and pressure, and they're not sedimentary because they're not particles that settle down. They're minerals that grew from this hot water. And I tell people that a whole lot of the mineral masses of mineral that you see on display in museums and rock shops, like all of those neat mineral veins from the Sweet Home mine, that have quartz and rhodochrosite and tetrahedrite and whatever else, they all grew from hot water, so they're hydrothermal mineral deposits. And a lot of what's on display at these shows, well, of course, there's those original hydrothermal mineral deposits, and then there's the stuff that has undergone oxidation and hydration under lower temperature conditions and derived from that. But minerals that we think of as occurring in those veins, again, quartz is probably the most abundant, and there's calcite and the other carbonates, fluorite, barite, a lot of the sulfurite and the other sulfides that occur in those. So I'm just thinking about those, wanting you to think about it, just to kind of set the stage for the rest of what I'm going to talk about. What I'm not going to talk about in any detail is some of what Terry was referring to about the understanding we have, which is really kind of a very simple idea, but it was Robert Hazen at the Carnegie Institution who really put this into clear focus, is that the kinds of minerals that we find on Earth didn't all exist in the original early Earth, that they have formed through, because the environments on Earth have been changing and the processes that form minerals have been changing, so that the very large number of minerals we have now wouldn't have formed in the first billion years that the Earth had cooled enough to form solid rocks and minerals. And as I think Terry referred to it, that one of the biggest changes that took place is when life that was photosynthesizing started pumping oxygen into the atmosphere, and then we had oxidation that was taking all these nice, pure, pretty sulfide minerals and turning them into a whole bunch of secondary carbonates and tungstates and everything else. And if you want to read more about this, Robert Hazen has published a lot of articles in things like Smithsonian and scientific journals. He has a very nice book called The Story of Earth, the first 4.5 billion years, and I recommend that book to you, okay? So just to keep that in mind about a lot of them, when I talk about some minerals here, I'm going to kind of refer a little bit to where in the stage of Earth evolution they may be formed. So I'm going to, and if some of you have seen some presentations I've given to a couple of the mineral clubs in Colorado here, you may have seen some of these slides before. So just thinking about minerals, okay, we know now, of course, that there are two things that distinguish each mineral from all the others. Its chemical composition and its crystal structure. And some minerals have pretty simple arrangements of both, like halite, simple chemistry, sodium chloride, a very simple cubic arrangement of the sodium and chloride ions that make it up. That's cool. I had to put in a picture of fluorite, since that's the theme of the show here. And once again, it's a little bit more complex than halite because it's got two of one atom and one of the other, but it's still got a fairly simple cubic crystal structure. Quartz has a bit more complicated crystal structure, which I don't think I have an illustration of, or maybe I do, but it's, simple chemistry and reasonably simple structure. Quartz can get a little more complicated. Some of it is just cosmetic because quartz occurs in a lot of different colors, and we give cultural names to them because they're used as gemstones, and people have always thought they're pretty, but of course they're all still quartz. It's taken a little bit more science to understand just what is going on in agate and chalcedony and in jasper, where the quartz is microcrystalline or cryptocrystalline. It's made of very tiny, often fibrous crystals. We know now that it's even more complicated because it's not just the mineral quartz. A lot of agate and chalcedony are intergrown with another very similar form of silica that has the mineral name moganite, and a lot of agate is really a mixture of quartz and moganite, but you need some pretty sophisticated diffraction techniques to determine that, okay? The next slide I'm going to show you, and I almost venture to say that this is something I saw out. Oh, good. I'm glad I didn't accidentally hit the wrong button. I saw in a public park in Spruce Pine, North Carolina, and it's a piece of artwork. And I just couldn't contain myself when I saw this, because I think this is the most wonderful, amazing, accurate piece of geo-art that I have ever seen. And I don't think, and hardly anyone has, to my knowledge, has seen, in the geological community, has seen this or knows what it is. I just thought this was absolutely wonderful. This relates to quartz, okay? And now, so I'll go to that. And I was walking around with a friend in this park, and Spruce Pine is kind of in the Smoky Mountains of North Carolina. I had been there once decades ago on a field trip from graduate school, where we went to one of the granite and pegmatite quarries. Spruce Pine is famous for mining quartz and feldspar both that are used for industrial purposes. Okay, so walking around this, and I was on a trip through that part of North Carolina and just had to stop in Spruce Pine to see what it was like 50 years later or whatever it was, and saw some kind of sculpture in the park, and I almost didn't walk up to it, but we did, and here is this thing, and it's by God. Let's see, the pointer, it is. You all know what that is from looking at it, no doubt. I know that many of you. It's the silica oxygen tetrahedron that is the fundamental building block of all silicate minerals, and it's made to scale. So there in the middle, this goofy thing doesn't want to point, but you see that white sphere, that's the silicon ion, silicon +4, actual size. And those hoops, and there are 4 of them, one you're looking at edge on and you can hardly see it, represent the 4 oxygen atoms that surround it. And so you have to visualize, those are supposed to be spheres, big spheres, and that's their circumference. But if they made them as solid spheres, you couldn't see through the crystal structure as well. So you have to envision them surrounding the silicon atom. So I thought this was so cool that they put this giant sculpture in that public park in Spruce Pine, North Carolina. Go there someday and see it. And if I could read it, or if I, here, let me give it, it's titled, it was made in June 2004. I'm just going to read the little label here. Can you hear me okay, I think? It's titled Beginning, is the name of the sculpture. Silicates are the most abundant minerals in the Earth's crust. Due to the world-class deposit of silicates here in the Spruce Pine mining district, Spruce Pine has become the global leader in mining. Mark Majoris Beginning, name of the sculpture. The silicate tetrahedron, SiO4, consists of a single silicon atom sharing 4 interconnecting oxygen atoms. Through the varying combinations of adjoining tetrahedra, do different silicate minerals result. Furthermore, through the addition of elements like aluminum, magnesium, potassium, chromium, and iron to the silicate tetrahedron, do we arrive at the wide spectrum of silicate minerals found here in Mitchell County. And I think, and that's a whole course in mineralogy right there in that paragraph. I love that. So anyway, that totally made my day to see that. That was just this spring. Anyway, so moving on to some minerals, okay. Once again, some minerals are pretty simple chemically, again, structurally, copper and silver both, okay. Chalcopyrite is pretty simple chemically. Now, it's one of those nice sulfide minerals that it forms within igneous rocks, but usually through hydrothermal solutions that have been percolating through them after they solidified. Chalcopyrite is probably world overall is the main form of copper mineral that is mined that accounts for most copper production. And it's also one of those minerals that if we didn't have all this nasty oxygen in the air that was oxidizing all our pretty sulfide minerals, there'd probably be weathered, eroded, lumpy chalcopyrite grains scattered all over the surface of the earth, and riverbeds would be all full of pretty shiny nuggets of chalcopyrite and pyrite and everything else. But in our environment, they all get corroded and rusted and oxidized, and we don't see them. So you have to get freshly mined specimens to see them in their pretty pristine shape. And a lot of these other nice copper minerals that we all know and love are oxides or hydrated oxides or carbonates, so they probably wouldn't exist without this atmosphere that's been messing up all those primary minerals and creating new ones. So cuprite, copper oxide, malachite, and azurite fall into that category. The copper's been oxidized and got CO2 and water mixed with it. And let's see. So I'm just going to talk about some of the mineral groups here that make up significant parts of our Earth, and now I'm kind of, I guess my thinking about the minerals here has led me to try to show you about how our understanding of minerals and the groups of minerals that exist has amplified and expanded over these last however many decades. So what we used to think of as some pretty simple minerals are actually very complicated groups that can vary chemically and consist of a whole bunch of minerals. Now, these are ones mineralogists have known about for a long time. Okay, the carbonates, and we know they can form in two different crystal structures. The aragonite structure is more stable under higher pressure conditions, but some atoms, some metals like barium and strontium and lead more naturally fit into that denser structure, and some like magnesium and iron more naturally fit into the less dense calcite structure. And of course, our favorite state mineral, which is on display here in the show in spectacular form, is one of those rhombohedral type carbonates with the lower density. Olivine is an important mineral in the earth, okay? We geologists and mineralogists like to call it olivine. Of course, gem people call it peridote when it's gemmy. Many of you probably know that it's olivine, for a start, is a series between the magnesium end member and the iron end member. Most natural olivine, including most of the mantle, is very iron rich. Is magnesium rich. So what we mostly have is the magnesium dominant form of olivine, which has the name forsterite. Phaolite, the iron dominant form, is relatively rare geologically. You find it in tiny crystals that have formed in cavities in volcanic rocks or deposited by hot springs, perhaps. So, olivine is kind of easy to understand. Just for the record, those faceted olivines and the grains in peridotes and the grains being held in the hand, those are from Colorado. Those are several carat size faceted olivines from one locality in South Park, which many of you probably know about, where you can find peridote grains like that, and some of which get up to 5 or more carats in size. Very, very rarely. Just a digression. So we go to the feldspars, which represent a significant part of all the rocks on Earth, and they get a little more complicated. There's different chemistry of the feldspars. You can have potassium and sodium and calcium dominant and others, and depending on the temperature they formed at and how slowly or rapidly they cooled. You get different crystal structure modifications, okay? I came across a really neat diagram illustrating, composition of feldspars can be represented in a ternary diagram, where you plot the composition in terms of sodium, potassium, and calcium, and textbooks will show that just as a black and white diagram. And someone posted this on Facebook, and I honestly don't know who created this diagram, but maybe someone here does, because I think it's way cool, and they actually put actual photographs of feldspar specimens on there, okay? So you may know that, there's a complete solid solution of the plagioclase feldspars between albite, the sodium end, and anorthite, the calcium end, and there's a mostly solid solution between sodium and potassium, but when those feldspars cool, they tend to separate out into different sodium-rich or potassium-rich feldspars, okay, which gives rise to things like iridescent moonstone, because you've got layers of the two different compositions separated, and way up at the potassium end we have microcline feldspar that forms at relatively low temperatures. This guy isn't always working, in granites, and you see there's a little bit of blue in there because that's where amazonite, which is special type with special coloring agents of microcline. Anyway, I think that's a way cool diagram, and if I could read the fine print on the edge, I'd probably know who created this. I'm going to show you one more in a bit that came from the same source too. But anyway, so there's, and for the most part, in the middle of that diagram, feldspars don't form with compositions in the middle of that ternary. So we either get plagioclase feldspars or the alkali feldspars here. Anyway, couldn't neglect feldspars. Show you a slide about beryl, which of course is famous for the various gem varieties in different colors, which you all know and love, okay? A lot of people will just, see aquamarine. They want to call it aquamarine. We mineralogists like to call it beryl, of course. But beryl is actually a group of minerals, a modest-sized group of minerals with several others that have the same crystal structure but have different metallic elements in them. So there's beryl at the bottom, beryllium aluminum silicate. There's an interesting one called basite, which actually occurs in very small amount in Mount Antero in Colorado, that has scandium instead of the aluminum. Pisatite, fairly recently discovered, has cesium and lithium in it, and there are three more, even more complex ones, okay? So the beryl group is an interesting group of minerals. Garnets are another, it's neat that minerals do occur in groups with this isomorphous substitution, so we don't have to learn the properties and formulas of 5,500 and whatever totally different minerals. Since nature puts them into nice groups, we can kind of learn about that group, and then that helps us understand the minerals in it. So garnets are, of course, a much well-known and beloved group of minerals, and a lot of those are used as gemstones. And once again, there traditionally have been 6 kinds of garnets that are fairly common and occur pretty frequently, but there are a lot more garnet group minerals that contain rather esoteric combinations of elements substituting in there. I didn't write them all down for you, but there are 8 more that fit in the garnet group, and then 14 more that sort of fit in the garnet group. And this is where I found another one of these diagrams, evidently created by the same person or institution. I just saw this a few weeks ago on Facebook. I thought this was way cool. So they're illustrating the colors that are commonly present for those main garnet minerals, pyrobalmandine, spessartine, which tend to have more solid solution between those three, and the other three, the calcium garnets, which tend to be greenish or brownish or yellowish shades instead of red, they also show more common solid solution. So Uvarovite's the cool one with the chromium in it and gives it the nice emerald green. So I thought that's a way cool diagram too. Let's see. So I'm just going to cruise through a couple of more successively more complex groups of minerals, okay, one of which is the zeolites, which we love to see at mineral shows, and those of us from Colorado here love to collect them on North Table Mountain over by Golden, and there are, maybe a dozen or so zeolite minerals that you'll commonly see in the displays at the shows that occur in India and elsewhere. And these are some of the most common ones, all of which actually occur on Table Mountain, I believe, here in Golden. But overall, last I counted, there were 103 different minerals in the zeolite group, which makes it quite a mess. That group of minerals is not exactly it's not the same exact crystal structure, but of course the thing that distinguishes it is it's this crystal structure with large holes within it, which allow ion exchange because water containing dissolved ions can percolate through it. It can be used for water purification or to even gases diffuse through them, and it can be used for some gas exchange too. So here is Table Mountain. I love North Table Mountain here. I was hiking up there last week, actually. These are a couple of the three most common minerals that you found here in cavities in the alkalic basaltic lava on Table Mountain, and there's a couple of our favorite specimens from India, some mesolite and stilbite. So just talking about the complexity of a group of minerals like that, so here is a small subsection taken out of MINDAT of alphabetically the first few minerals in the zeolite large family, many of which have names that, well, I'm certainly not real familiar with. Alflarsenite, I think that's probably named after someone. Anyway, and there are a whole bunch more, all 103. Another group of minerals that's more complex than most people realize is turquoise. We think of turquoise as being a single mineral. It's a copper aluminum phosphate hydroxide hydrate, okay? But turquoise comes in different shades of color, ranges from deep to pale blue and greenish shades, okay? And there's a reason for that, because it's a group of minerals too. And some of these contain more or less copper, and some of them contain iron and zinc and other things, which give them generally less attractive colors. In theory, some of them, like planarite, don't contain any chromophore transition metals at all, and they can be almost colorless. So turquoise is a small mineral group, okay? Tourmaline, again, a group of minerals in which we're often discovering new, from their chemical composition, new species. The traditional common ones are elbaite, which is most of the colored gem tourmaline, and dravite, the brown magnesium-rich tourmaline, and schorl, the black iron-rich tourmaline. And we've realized a lot of what looks like elbaite is really lidocotite, which contains calcium instead of sodium, and so on and so forth. But again, there's like 45 different mineral species known in the tourmaline group now. But the colored gem ones are just beautiful. And another really, really complicated group are the amphiboles. And when you go to college and you take a first course in geology and you study minerals, you learn about a few amphibole minerals. You know, they're a little different than the pyroxenes, and you learn about things like actinolite and tremolite and hornblende and maybe riebeckite, which is blue-black sometimes. Some of those things occur in Colorado here, like the riebeckite from St. Peter's Dome area, which is in the upper right. But there's a tremendous opportunity for variation in the chemical composition of the amphiboles. So now, last I counted, there were 209 different amphibole minerals, and once again, here, and what we used to think of as hornblende, of course, is no longer considered a single mineral, but there's ferro, fluoro, hornblende, et cetera, et cetera, et cetera. So I don't know what to say about that, except nature is complicated. And I think this is my last slide, and just that, you know, another group of minerals, not that makes up major parts of rocks in the earth, but there are a lot of these, what we call accessory minerals, that contain rare metals and rare earths and everything else. One is the pyrochlore group of minerals, which are a group of somewhat complex oxides. Pyrochlore itself used to be considered one single mineral. Now there are a whole different bunch of pyrochlore minerals related to betaphyte and microlite and a lot of others. So I guess I'm taking joy in the complexity of the mineral world here, and that we're understanding it better and better each year. And I think that's the end of my presentation. Thank you.
All right, thank you, Pete and Terry. I agree with you. I think the zeolites are a mess, for sure. We do have time for some questions. Do we have anybody out there who would like to ask either Terry or Pete something from their great presentations? Could you restate the question?
Yeah, so the restate question is that is there something about hammered gold, which we would call worked gold, that can tell us about the date? And I have to think about that one. I don't, you know, my first impression would be no, but in fact it's complicated enough that I wouldn't. But it's interesting that the methodology to be able to look at this came about not because of a geologist worrying about a gold sample, but there's such trafficking in gold artifacts that are frauds. And somebody said, oh, you know, maybe we can do this. And it was actually a bunch of chemists. And now we have instrumentation that a tiny speck of gold, we can tell you when it was melted. And I will tell you that in the journals, about 75% of gold artifacts that are trafficked to be antiques or fakes. And it gives you at least a frame of how often we as humans, seek to fake things. 75%. Yeah. That's correct. So I don't think you can get to the, so you lose it. Gold's a little different than a billiard ball in that a billiard ball is largely incompressible and gold is so ductile. And so actually what you just said is a really cool thermodynamics problem, by the way. But the fact of the matter is that, I have to think about it. You know, if it was copper, I could probably answer more affirmatively because it causes twinning. I am not positive about gold. I don't know.
So if we take two billiard balls and clack them together real hard 1,000 times, can we raise the temperature high enough to melt our billiard ball?
So again, you probably would radiate and lose enough. But it is interesting that there's a classic experiment that looks at doing this with a shake table, which they can actually measure the temperatures go up. It's again, every person that took high school physics got the equation, right? You got the kinetic energy equation, and so you can do it. But it's hard to sit down and do the experiment, but it's actually quite observable with the way we can measure things today.
Interesting. Any other questions? One thing I was wondering about when you showed the 4.5 billion year time scale, how I was wondering when the oxygen level increased so dramatically at a 1.5 billion years ago, what caused that?
So I think Pete could probably answer this question too. Is what we know is that we had single cell forms of life before that, but frankly, the way I would describe it is we invented sex at 2.8 billion years, and that allowed a much more efficient way for life to propagate. And so as soon as it began to propagate, then you develop, it's full photosynthesis, and so you had an explosion of algae. Algae is the first zygote, is the first sexy creature.
So it's a biological cause.
It is.
Very interesting. In fact, biology does so much for the mineral world. It helps to form many of the minerals that we see today, even more on the microscopic scale, I suppose.
And again, I think that people what I'm amazed is that the amount of literature that's coming in today, where people are looking at deep cores in the earth and things like that, and they're still finding what are unsexy life forms. But it is amazing that the energy equations associated with life allow it to exist almost everywhere on Earth.
Another thing that struck me was everything is pretty much made of a very small number of types of elements. We know of only, 117 or something.
119.
119,
sorry. Skip that one.
119.
We don't want to shortchange Lawrenciumite.
But that is all we know. As time changes, or as things change, will we find more and more chemistry in the world?
So you'll always find more chemistry, but in terms of elements, you do have some fundamental limits. And so as we're talking about, you're trying to hold together this nucleus, and there's these competing forces of protons want to push each other away, but they're held together by a nuclear force, which is partially with the neutrons there. And frankly, if you look at quantum mechanic calculations, we probably can't see any elements that are larger or heavier than 121, 122 protons. And so we're probably kind of done with that. We'll spend lots of money trying to make those heavy elements, but their half-lives will be a fraction of it.
Because we have uses for them?
No, because science is good.
Okay. Any other questions? Well, gentlemen, thank you very much. That was fascinating.